have a resistor inductor, which was also there in the previous case, which we did in type 1. But the difference was that in earlier case you had a unit step signal, and in this case you have a ramp signal. So let's see how the circuit B is when you have a ramp signal. Again, ramp signal, unit step signal, delta signal, this indicates your sum is of a Laplace transform. So let's directly start with t greater than 0 plus condition. So for t greater than 0 plus condition, the circuit will be plus minus r of t minus 3, 5 ohms, 2 Henry. So let's convert your network into a Laplace network. So convert into Laplace domain. So when you convert to Laplace domain, you should know that this basic formula for r of t minus a. Before r of t minus a, you should know r of t. R of t is given as 1 upon s square. So when I talk about r of t minus a, the extra part is minus a, which is written in the form of exponential. So minus has been removed. So remaining part is r of t. R of t Laplace is 1 upon s square. If it can be r of t plus a, then it will be plus a. So it will be e raised to plus s into the remaining part is r of t. So r of t Laplace is 1 upon s square. So now let's convert everything into the frequency domain. So it will be plus minus e raised to minus 3s upon s square. There is no change in resistance, but the inductor changes because inductor changes from L to Ls. So the value will be added with a term known as S. So that everything gets converted into a Laplace domain. Now obtain the equation here, I of S. So apply KVL. Over here, make it a point you don't apply the voltage formula of inductor LDAV. That can only be obtained when your equation is in time domain. This is in frequency domain, Laplace. So please don't do it. So it will be adding 5 plus 2s I of s equal to negative, so it will be e raised to minus 3s upon s square. So your I of s is equal to e raised to minus 3s upon s square 2s plus. So as we have discussed earlier, we need to neglect the exponential part, and the remaining part we need to apply the partial differentiation. Let's apply the partial differentiation for the remaining part. 1 upon s square 2s plus 5. So it will be 1 upon s raised to 1 plus b upon s square plus c upon s square. So this is when we have s square. This is the format where you write. It will be s cube. It will be a upon s, b upon s square, c upon s cube. So let's find individually a, b, and c. So this kind of sum can be solved in this manner. For a, you have in denominator s. So compare with this term, which term you don't have it. So you don't have any s. So you don't have s plus 5. Why s? Because this was s square, s into s was already there. B. So you have s square, which term we are not having here? 2s plus 5. C. Which term you are having? 2s plus 5. Which term we are not having? S square. So make a bracket. Okay. This will be 2s square 5s b 2s plus 5 c into s square. So your s square will be multiplied, you get 2a. This will be cancelled. This will be 1c. Next, your s term will be 5a plus 2b. Next, your number term will be 5b. So if you compare with this, you have 0s square 0s plus 1. So compare it, 2a plus 1c equal to 0, 5a plus 2b equal to 0, and 5b equal to 1. So if you equate all the terms, my dear friends, you'll get the value for a, b, and c in that manner. So that is the way you get this equation for the following in this manner. So let's compare it. So value of a, b, c, which you will be getting it at the end after using a scientific calculator, b, b, and c. So a will you will be getting it minus 0.08, b you will be getting it 0.02, 0.08. So put the values of a, b, and c. So let's get the equation for I of s. The equation for I of s will be e raised to minus 3s will be as it is. A is minus 0.08 upon s, b is 0.2 upon s square, plus c is 0.08 upon 2s plus 5 in this form. So this you can also modify it before putting the equation. You can write it as, if you take it 2 common, you can write as 2.5 in this way, so and so, right? Because rule is that for applying Laplace, you need to have the coefficient as 1. The coefficient should be 1 in this form. So I of s is equal to, multiply this, e raised to minus 3s upon s. So 0.2 e raised to minus 3s upon s square. 0.08 e raised to minus, again directly converting into it, no division, nothing, that I can see that is very simple. After getting this equation, my dear friend, applying inverse. The reason of applying inverse Laplace is that ultimately our main goal is to find I of t. The equation which we have is I of s. So we'll be getting I of t only when we get the equation of I of s in such a manner that we can apply the inverse formula to it so that we can obtain I of t. So let's apply I of t, my dear friends. So your I of t will be, the constant is minus 0.08 e raised to minus 3s upon s. So upon s, that means it should be u of t, and e raised to, along with that, that shows there's a delay of plus 0.2 upon u of s square, that means it's very integrated r of t, and e raised to minus, that means it is minus 3 plus 0.08. So upon you have 1 upon s plus 2.5, so it is e raised to minus 2.5 t into u of t. So exponential, you have e raised to minus 3, so e raised to minus 3. So that's the equation which you got after applying the inverse for I of s. Making sure, my dear friends, to revise the formulas which have been discussed in some type number 1 for this chapter before doing the sums. If you haven't seen that video, please make sure that you see that type, that is the main part of this chapter. All the basic formulas have been discussed in that. Okay, signing off. Thank you so much, guys.